sometimes when we're looking at proving conjectures and statements, it can actually be quite tricky to come about these things, particularly when we're looking at things like counterexamples and direct proofs. Sometimes there's just too many ways to do it. What we have to do is come up with a contradiction to help us in our steps. So what I want to talk about in this video is looking at proof by contradiction. Now this all comes about from the fact that we said a second ago, sometimes a statement can be incredibly difficult to prove. So let's imagine I give you a statement, prove that there are no numbers n and m belonging to the set of integers that satisfy 3n plus 21m equals 137. That there would be incredibly difficult to prove, especially through trial and error, as there's an infinite number of integer combinations that we would have to check. So it is going to be really, really tricky to prove, or really, really tricky to find a counterexample to. So the way that we're going to avoid doing this is we're going to use a technique which we're calling proof by contradiction. And that comes about in a set format. In order to work with proof by contradiction, there's a couple of steps that we want to follow. The first thing we want to do is actually assume that the original statement is false, using a technique called negation. So for example, if the original statement was of the format, if P then Q, the contradiction we would use is we assume P but not Q. So what do I mean by that? Well, a couple of examples. Let's imagine I give you the statement that if m is an even integer, then m plus 2 is even. My contradiction to that would be saying, assuming that m is an even integer, then m plus 2 is odd. So I've taken the if and made an assumption, but then I've negated and reversed the other part of the statement. Second example I've got there, if x minus 5 is equal to 0, then x equals 5. Well, the contradictory statement for that one that we would use is assume x minus 5 equals 0, then x cannot equal 5. And we would use that to try and prove the statement that we want. Once we've done it, we then start to make a series of deductive steps until we then contradict the contradiction. Once we've contradicted the contradiction, that contradiction is false, which means the original statement is true. So it almost sounds like we're going back on ourselves for the sake of going back on ourselves to prove going back on ourselves is wrong. But actually, it makes logical sense. By reversing the statement and contradicting it, and proving this contradiction is false, the original had to be true. We eliminate having to try every value, for example in the previous statement, and we then limit it to a point where we can actually fairly quickly and easily prove something. Easy way to demonstrate this is with a couple of examples. So let's say that I want to prove that if mn is an even integer, then at least one of m or n is even. First thing we have to do is come up with a contradiction. So what I'm going to say is that I'm going to assume that mn is even. So we assume mn is even, then neither of m or n is even. So we negate that part of the statement. If this is true, at least one of them is even. So what we're going to say is if we assume nn is even, and that neither m or n is even. So what we can then do is with this assumption, say that fine, what that means is that m has to take a format of 2k plus 1. That will always give me an odd number. And n is going to take a format of 2p plus 1. So it's also an odd number, but I'm calling it 2p rather than 2k so that I can take into account the fact it's not going to be the same integer value, or it may not be the same integer value. If I then take the two of these and I use mn, what I'm going to get is 2k plus 1 times 2p plus 1. If I expand that bracket out, I'm going to get 4kp plus 2k plus 2p plus 1. Now, if I focus on just this section here, what I'll notice is that each term there has a common factor of 2. So I can then say, fine, if I take it a common factor of 2 there, I'll have 2 bracket 2kp plus k plus p and then plus 1. Now if I look back at what I did for m and n, 2 times something plus 1 gave me an odd number. Well, in this case, I've got 2 times this whole bracket here. Let's imagine I'm going to represent that whole bracket by t. What that means then is it takes the format of 2t plus 1, which is an odd value. So what I've actually done there is I've contradicted this contradictory statement I've said by assuming that m times n is even, and neither of them are even. I've actually proven that it's odd. So I've contradicted my contradiction, so therefore my original statement is true. I've proven what I wanted to prove by proving that it not being true is not true, if that makes sense. It's quite a step to go through, but actually when you get in the swing of it and you start going, you'll make it no problem. You just have to remember certain things as well. So for example, format of an odd number being something along the lines of 2k plus 1 or 2p plus 1. Format of an even number just being 2k or 2p. Using them as part of our work, that is vital to some of the stuff that we're going to be doing. Let's take another set here. So let's take another example here. So what I'm saying here is that I want to prove that there are no numbers n and m belonging to the set of integer values that satisfy 3n plus 21m equals 137. So I first have to start by coming up with my contradiction. So what I'm going to do is I'm going to make my contradictory statement. I'm going to say that for all values of n and m belonging to the set of integer values, this statement, 3n plus 21m equals 137, always. What that does is that contradicts the original statement of there are no numbers in there, because now I'm assuming that it works for all the numbers. So if I now work with the 3n plus 21m equals 137, you'll notice that 3n and 21m have 3 as a common factor. So if I take that out and have 3 bracket n plus 7m equals 137, and I then divide across by 3, what I end up getting is that n plus 7m is equal to 137 over 3. Now 137 over 3 as a mixed number is 45 2/3. Now if n is an integer and m is an integer as stated here, what that then means is that n plus 7m also belongs in the set of integer values. You can't combine two integers and get a decimal or a fraction. However, what that then means is that n plus 7m cannot equal 45 2/3. It cannot equal something with a fraction in it. It has to be an integer result. So what I've done is by assuming and saying that for all the values belonging to an integer set of numbers, I am getting a fractional answer. I've contradicted myself. So I've actually then contradicted the contradiction. My original is true. So I've proven that there is no number n and m belonging to that set of integer values that satisfies 3n plus a 21m equals 137. Proof by contradiction is one of those processes that if you can get that first statement down and then start to think about the format of the material you're working with, that's when success follows. But if you manage to get yourself totally confused and can't think how to write the contradictory statement, that's when trouble begins. So go and start to think about that before you do anything else. What can I write the statement as in order to contradict myself? And a big part of that is looking at this and looking at the wording. If M is this, and then assume. If, then assume. If puts the condition on it as part of the statement. Assume as part of the contradiction means it is the case. If you can put that across, what that means is you'll have the contradiction by assuming that it's true no matter what, and then your proof by contradiction can come through as you'll contradict yourself throughout. So try not to get yourself confused with that and get a bit of practice at taking the if statement and making it an assumption. Doing that helps you to write the contradiction and will help you with your work through this.